So as we know that uh, for communication in the network, the protocols are the foundation of your data communication. So for this reason, they have been a target of your threat actors for a very long time. So the cybersecurity analysts must understand how threats or the vulnerabilities are used by your threat actors for some common protocols in the cybersecurity or in your network security. So in this module or in today's lecture, we are trying to overview the layer 3 protocol from your TCP/IP suite. That is your network layer, where the IP packets are, used to travel from, one network to another network or one device to the another devices, and also the layer 4 protocols are layer 4 the protocols like your TCP and UDP. We'll look into the header field, how the header field looks like exactly, and what are the fields are basically a attacker looks into that header that we'll try to discuss in today's lecture. So in this, we'll try to discuss the IP PDU details and your the IP vulnerabilities and TCP UDP vulnerabilities, because these are the most important one for any of the attackers for analyzing attacker or the defenders. So in this IPv4 and IPv6, we'll try to discuss the IPv4 in detail, and the similar process will be there for your IPv6. So first we'll try to discuss this IP, the PDU details. So in this, the IP was designed as your layer 3, that is Internet Protocol. So this layer 3, this IP is a layer 3 connectionless protocol because it don't establish any connection between your source and the destination. So it provides the necessary function to deliver a packet from a source host to a destination host over an interconnected system of your networks. So the protocol was not designed to track and manage the flow of your packets from inside network to your outside network or outside network to your inside network. So these functions of your IPv4 or IPv6, if required, are performed primarily by your TCP connection or TCP at layer your 4 or UDP at layer 4. So this IP, makes no effort to validate whether the source IP address contained in a packet actually comes from that legitimate source or not. It don't validate, but for this reason, the threat actors can send packets using a spoofed source IP address. So in addition, the threat actors are the malicious nodes in the network can just tamper with the other fields in the IP header to carry out their attacks. So therefore, it is important for security analysts to understand the header field of your layer 3 protocol and your layer 4 protocols, that both in IPv4 or IPv6 or a TCP UDP packet. So that is most important part one. So this is for any of the threat actor, as we said, it is not going to establish any connection is one reason. Another one is any system in the network, they don't validate these IP addresses or IP packets. So we'll see the header field of your the TCP IP version 4 packets. So in this, if you find that there will be, 1 byte is used for some version purpose and 2 bytes are used for other services. We'll look into this one by one, and 3 bytes are different. So total it uses, there are 10 fields in this IPv4 package which use for a different services purpose in the package. So first you see that the version will be there. So this version indicates whether the packet is IPv4 version or IPv6 packet it is. So This contains a 4-bit binary value that's set to generally 0100, uh, 0100 to indicate it is IP version 4. If it is IP version 6, then the bit version value will be changed. It is 0110 it comes to represent IP version 4. And the second field is your internet length field, the internet header length field. So this is also a 4-bit field that containing the length of your IP header. So the minimum length of your IP header is actually 20 bytes. The minimum length of this internet header field is 20 bytes, and maximum it depends upon how much the load that the packet is carrying from source to destination. And the next important service is in this important field in this IPv4 packet header is your the differentiated service, or we call the DS services. So formerly this is called the type of your service, TOS we used to say, type of your service field, but the DS field in an 8-bit field used to determine the priority of your each packet. So the 6 most significant bits of the differentiated service field are the differentiated service code point, we say DSCP, differentiated service code point. Uh, and the last 2 bits are the explicitly the congestion notification bits. So total it use there's the 2 bytes used for your differentiator search purpose, and your 1 byte used for your DSCP, and 1 byte used for your the congestion purpose, exploiting this congestion notification. So then it is having a length of total length field in the IP header. So this specifies the length of your IP packet, including the IP header and the user data. So the total length field is 2 byte. So the maximum size of your IP packet is, the maximum size to represent with this, 2 bytes is your 65535 bytes, the maximum size of your packet. So, however, the packets are much smaller in practice, but the maximum size will be your 65535 bytes. And next, important field is identification field. So, in this, the identification field, as an IP packet moves through the internet, so it might need to cross a route that cannot handle the size of your packet. So the packet will be divided or fragmented into smaller packets and reassembled it later at the destination site. So these fields are used to fragment and reassemble packets, the fragmentation done on source side and reassembling done on the destination side. So for that, how many these packets are divided into how many packets, that will be identified by this identifier, and we call the sequence numbers given to each part of your packet. So then you will have the time to live field. So it contains 8-bit binary value that is used to limit the lifetime of your packet. Suppose if the time to live is set to suppose 8, that means, as you know, the packets travel from through internet from source to destination in a hop by hop manner. So for every hop, when it is reaching, it will reduce from 8 to 7, then 6, and when it reach to 0, after that the packet will be dropped from your network. So it will keep that the packet should not be in the network after a certain period of time. If it is in the network, then congestion will occur. So to avoid the congestion or loop free, it will reduce. So that is the use of time to live. So this packet, sender sets this initial time to live value, and it is decreased by one each time the packet is processed by a router in the network. So if the TTL field determinants decrements to zero, then the router discards the packet and sends an internet control message protocol time exceeded message to the source IP addresses. A next important field is your protocol field. So this field is used to identify the next level protocol, the next level protocol. So it uses the 8-bit binary value, which indicates the data payload type that the packet is carrying, or which enables the network layer to pass the data to the appropriate upper layer protocol. So it indicates what is the upper layer protocol it is requiring, means whether it is using the TCP connection or the UDP connection. So for TCP connection, includes certain values for TCP connection, like it includes the value 6, and for UDP connection, it includes the value 7. That means this packet is belongs to the connection oriented service or connection less service will be identified with this protocol. So then comes to the header checksum part here. So in this header checksum, this value that is calculated based on the content of your IP header, so which is used to determine if any errors have been introduced during the transmission of this packet from source to destination. So there may be the chance that because of the attacker, if this header, checksum goes wrong, that means that packet is the modified or altered by any of the attackers. Next important one is your source IP address. As we know, it uses the source's IP addresses, that private IP address, and it consists of your 32-bit binary value that represents the IPv4 address of the packet, and you are having the destination IPv4, and finally you're having some optional padding is there in this case. So this optional padding field, this varies in the length from 0 to a multiple of your 32 bits, because if the option values are not a multiple of your 32 bits, then zeros are added or padded to ensure that this field contains a multiple of your 32 bits in this case. So this is the general fields of your IPv4 packet. So when you did the what you call uh, the lab using your Wireshark, you might examine these fields, the version and internet header length, then for that packet which service, which protocol it is using, whether TCP or UDP, that you might have found an internet control protocol version in that. So we'll just try to check it out this to find how it worked, and what you observed in your lab. Let us try to find it out. So let me just play this video for you. It will help to. Let me just play this. Uh,
Screenshot from a Wireshark packet capture, and you can see that the And you can see that the second packet that's been captured has been highlighted. And then in the packet details window, the network layer information has been expanded to show us all of the things happening at the network layer. So let's see what's happening in this particular packet that we're examining. We can see that, first of all, the network layer protocol or internet layer protocol that we are dealing with,
version 4, IPv4. We can also see that the source IP address was 192.168.1.109. You can see it also highlighted up here in the packet list window area, and that the destination IP address was 192.
So you might have observed this, right, in Wireshark while capturing the packet. The first field, it shows that version 4, whether it is IP version 4 packet or IP version 6 packet. And then the header length, as we said, the minimum length of this IP packet header is 20 bytes, and it may increase based on the user data if it is there in the packet. So this is simple a TCP IP connection packet. So the header length of this packet is your 20 bytes here, and here you are using the differentiated service field. So this differentiated service field is basically used for giving what kind of services it is going to use, whether it is the DSCP or the congestion control notification part that is given, and the total length is 52 bytes here. That means any attackers, they can simply understand that there is no user data in this packet because the size is only 32 bytes here. That means this packet is simply using for connection establishment from source and destination. Okay, and we have seen the fragmentation, whether this packet is divided into smaller chunks or not. If not, then there is don't fragment. This means it is not divided, it is a single packet itself. So you can see this
168.1.1, and we can also see that up here. We can see that at the higher layer, this is a TCP protocol packet. But if we limit ourselves to just the IPv4 fields or the IPv4 information, we can see the different types of control information that's contained in every IPv4 packet. For instance, the version number, which is 4, identifying this as an IPv4 as opposed to IPv6 packet. The header length
of the IPv4 packet. Let's take a look at two more screenshots of Wireshark packet captures, and we'll see some similarities and differences. The next screenshot shows us that now we're looking at the 8th packet captured. The packet's source IP address is also 192.168.1.109, and the destination IP address is 192.168.1.1, except this packet is an HTTP GET request. So this is a request to a web server located at 192.168.1.1. You can see that the network layer or internet layer information has been expanded, that it's also the IP version 4 protocol, and that we have similar information in the different fields. Notice under the total length field that this packet is 411 bytes compared to the previous packet, which was only 52 bytes. You can tell that this packet has a lot more information, or is a much larger packet than the previous one. If we look below the Internet Protocol version 4 information, we can see the TCP information, and then below that there's Hypertext Transfer Protocol or HTTP protocol information in this packet as well. I'll move forward to the next packet, and you can see that this packet is the 16th packet captured right up here. It's also from host 192.168.1.109 to host 192.168.1.1, except this is the ICMP protocol. You can see from the information in the packet list window that this is an echo or ping request. If we look in the Internet Protocol version 4 information in the details area, we can see some minor differences. The version is still 4. The header length is still 20 bytes. But we can see that the flags are slightly different, and that the protocol field is now set to 1, indicating that the data portion of this packet is an
that we have similar
ICMP protocol
information in the
message.
different fields.
Notice that in the details window at
under
the
the
bottom
total
here
length field
is an
that this
expanded
packet
area
is
to look at the
411 bytes
header
compared to
information
the previous packet,
specific
which
to
was only 52
ICMP.
bytes. You can tell that this packet has a lot more information, or is a much larger packet than the previous one. If we look below the Internet Protocol version 4 information, we can see the TCP information, and then below that there's Hypertext Transfer Protocol, or HTTP protocol information in this.
Yeah. So let us check the header field of another version that we try to realize that the version of your IPv4 packet, sorry, V6 packet. So in this, there is 8 fields in this IPv6 packet header. So as you can see in this the figure, that again the version, it uses that the 4-bit binary value to represent the version of this packet. Then the traffic class is there. So this traffic class field uh, basically used the 8-bit value, or 8 bits are used in this field, which is equivalent to your IPv4 differentiated service fields, and your flow label field that uses the 20-bit field that suggests that all packets with the same flow label receive the same type of handling by your routers in the network. And next comes to your payload length field. So this uses a 16-bit field, indicates the length of the data portion or your payload of your IPv6 packet. And it's having the next header field. So it uses this field uses the 8-bit bits, so which is equivalent to your IPv4 protocol field. So it indicates the data payload type that the packet is carrying, enabling the network layer to pass the data to the appropriate upper layer protocol. And there is a hop limit is there. It is similar to your time to live in the IP version 4. So this value is decremented by a value of 1 by each router that forwards the packet. And when the counter reaches to 0, the packet is discarded from the network, discarded by your router. And the ICMP version 4 time exceeded message is forwarded to the sending host. So which indicating that the packet did not reach its destination because the hop limit was exceeded. And see the IP version 4, similar to IP version 4, your source IP addresses and destination IP addresses use the 128-bit identification that identifies your IP version 6. So this IP v6 packet may also contain some extension headers as the optional field that provides the optional network layer information, that is the extension header or the optional and are placed between your IP v6 header and the payload. So this is the header field of your IPv6. So the rest, the details, how it is going to work, that you will check it out in our, the research side. So next we'll try to see what are the vulnerabilities are there in this IP packet. We'll try to check it out. Yeah, these slides which we just explained the topic. So what are the vulnerabilities are there in this IP version 4? That means there are different types of attacks that target the IP addresses. So the in this table you can see that the ICMP attacks. Why we use the internet control message protocols? It is used for pinging purpose, whether the destination is reachable or not. So the threat actors, they use this ICMP packet, echo packets, to discover these subnets and host on a protected network. What are the different subnets are there in that network, and who are the hosts are there? To check it out this. So by using this, the ICMP packets, the threat actors, they try to generate the devious flood attack, that is denial of service flooding attack, and to alter the host routing tables. When they try to alter this host routing table, all the route will be changed to the attacker side only. So any packets comes from the subnets or the host on the network, that traffic is simply diverted to the attacker side. So attacker can get all the packets information, and then trying to use this Wireshark or TCP dump tools to analyze that which version of this packet, and whether any load is there, user data is there in that packet or not, that can be analyzed easily. So another type of attack is your denial of service attack. So this threat actors attempts to prevent the legitimate users from accessing information or the services from servers or from other hosts. And another one is distributed denial of service attack. So this DDoS, distributed denial of service attack, which is similar to a DOS attack, but it features a simultaneous and coordinated attack from multiple source machines. And next one is the address spoofing attack. While the address resolution protocol is used to build what you call the layer 2 protocol table, that is your MAC address, which are getting from all the devices in the network to build the address, the address table. So during that time, this attack can be take place. So threat actors spoof the source IP address in an attempt to perform the blind spoofing or the non-blind spoofing to get the MAC addresses. And another vulnerability of this IP is man in the middle attack. So here the threat actors, they just position themselves between source and destination to transparently monitor the packets and capture those packets and control the communication between your source and the destination. So they could simply eavesdrop by inspecting the captured packets, or they may become as an active attacker. When they become as an active attacker, they can modify the packets. So when they modify the packet, it is possible to divert the route from source to the destination side. So another one is the session hijacking attack. So the threat actors again access to the physical network and then use the man in the middle attack type to hijack the session which is currently existing in between your source and the destination. So these are some of the vulnerabilities of your IP version 4 or IP version 6. So let us see this one by one, how it is going to be work out for the attackers. See here, there is an attacker here and there is a victim in this case. So the first one is your ICMP attack, as we said. So why we use this ICMP packet? Why we use this ICMP packets in the network? Yeah. It is basically used to ping the destination side, whether they are reachable or not reachable. So this ICMP was just developed to carry the diagnostic message and to report error condition when the routes, routers are your host and the ports are unavailable. So these ICMP messages are generated by the devices in the network when a network error or the outer outage occurs. So the ping command is a user-generated ICMP message that called an echo request. So that is used to verify the connectivity to the destination side. As so, the threat actors use this ICMP for the reconnaissance and scanning attack purpose. There are two different attacks are there. One is your reconnaissance attack and your scanning attack. So reconnaissance means, as said, it is trying to gather the information about the victim. So generally sends this ICMP echo request packet that is spoofed to the victim. Then victim will reply if the reachable, if the victim is reachable, reply. So in that reply, the attackers can get the information. What is the IP address? What is the MAC address of that victim? And which service the victim is using, that is whether TCP service or HTTP service, what kind of services are used, that will be easily identified this. So this, as we said, that is gathering the sorry, the reconnaissance information, and after the scanning attack means the getting the which ports are open and which ports are closed. So based upon your port number, it is easily identified by your attacker there whether they are using TCP service, UDP service, FTP service, or SSH service, which service that they are using. So this enables them to launch the information gathering attack to map out a network topology and discover which hosts are active and identify the host operating system and determine the state of the firewalls. So threat actors also use this ICMP for distributed denial of service or denial of service or distributed denial of service attack. So we'll see here in this figure, if you see that the ICMP version 4 and ICMP, it may be your version 6 are, susceptible to similar type of this attack. So upon giving this request to this victim is replied with this echo reply packet after that ICMP request. So it is a continuous process. So by sending this ICMP echo request continuously to victim, then victim will be busy with this attacker only. So victim will not provide any service to any other users, suppose legitimate users. If any legitimate user is there, another computer here, so if they try to connect with this, so your victim will give the denial of service because your victim is busy with the attacker itself. So this we call the ICMP attacker, so making the user busy. So in this ICMP, this echo request and your echo replies are used to perform the host verification and your denial of service attacks, whereas the ICMP sometimes gives the unreachable. So this is used to perform the network reconnaissance and the scanning attack purpose. And the ICMP mask reply is used to map the internal IP network, and the ICMP redirect packets are used to lure a large a target host into sending all traffic through a compromised device and create a man-in-the-middle attack. And ICMP route discovery packets are used to inject the bogus route entries into the routing table of your target host. So the networks such as um, the network should have a strict ICMP access control, the ACL, filtering on the network edge to avoid this ICMP probing from the internet. So security analysts should be able to detect this ICMP, the related attacks by looking at captured traffic and log files. So in the case of large network security devices such as your firewalls and your intrusion detection systems should detect such attacks and generate alerts to the security analysts that some unusual ICMP packets are coming from the different user or host in the network. So this is the ICMP attack type. So yeah, these are the different packets which we just said. The echo packets are used for your DOS attacking purpose. Unreachable packets are basically used for your reconnaissance and scanning purpose, scanning the ports. Mask reply, your redirect packets, and the route discovery packets used for different tasks. So the attackers always try to use these packets for attacking a host or the network in the in the attacking mode. So let us see this. The amplification and reflection attack is one type which uses this ICMP request. So in this amplification and the reflection attack, the attackers or threat actors often use the amplification and reflection techniques to create the denial of service attack in this. So in this example, if you see how the amplification and the reflection techniques called the we call the smurf attack is used to overwhelm a target host here. So if you see here, the first the threat actor do the amplification attack in such a way that by sending the threat actor forwards this ICMP echo request by using the source as your victim's IP address. Source is as a victim's IP address, not the threat actor's IP address. So the victim's IP address is used in this ICMP packet as the source address. So then when this source, when this packet comes to your router checks the header field of this packet. So in that header field, it finds what is the source IP address. The source IP address is the IP address of this victim, correct? So then host assumes that, okay, this packet is originated from a legitimate user in the network. So this message contains the source IP address of your victim, and in the reflection, these host all replies when it goes to ICMP packet. In that packet, if the destination is suppose 255.255.255.255, it is a flooding. So this packet is going to all the hosts, those who are there in that network, and every host assumes that this packet came from the victim itself. They don't assume that it is coming from the threat actor. So if the victim's IP address is suppose 192.168 dot or 1 dot suppose 15, so then this victim source IP address used by this threat actor. So here in this echo packet, it uses that 192.168.1.15. So upon receiving this packet by this host, they assume that the user is legitimate user only. So then they try to give the response back. So that is your reflection. So these hosts all reply to the spoofed IP address of the victim to overwhelm it. So here you just note that the newer form of this amplification and reflection attack, such as your domain name system based or DNS based reflection and amplification attacks, and your network time protocol, that is NTP amplification attacks, are now being used. So these threat actors also use the resource the exhaustion attack. So this attack consume the resources of a target host to either to crash it or to consume the resources of your network. So this is what it happens. So in address spoofing attack, as we discussed during the address resolution protocol, it can be either the non-blind spoofing or your blind spoofing can be done here. So how it will be do? Yeah, this is what we just discussed. So this address spoofing attack is one vulnerability of your IP. So there you find that the IP addresses spoofing attack occurs when threat actor creates packet with false source IP address, as we just said in the looked in the previous slide. So this source IP address information to either hide the identity of the sender or to pose as another legitimate user from that network. So the threat actor can then gain access to otherwise inaccessible data, or the security configuration files will be accessed. So this spoofing is usually incorporated into another attack, such as the smurf attacking. So the spoofing attacks that can be non-blind or your blind kind of your attack. So what happens in the non-blind attack? If you see, so in non-blind, the threat actor can just see the traffic that is being sent between the host and the target. So the threat actor uses a non-blind spoofing to inspect the reply packet from the target victim. So non-blind spoofing determines the state of your firewall and sequence number predictions. So it can also hijack an authorized sessions in non-blind spoofing. Whereas in blind spoofing, the threat actor cannot see the traffic that is being sent between the host and the target, but blind spoofing is used in denial of your service attacks. So in Mac address spoofing attack, which is are used when the threat actors have access to the internal network. So threat actors alter the MAC address of their host to match another known MAC address of a target host, and then try to act as a legitimate user. So let us see that with an example. So in this case, there is a server here. Server is using the MAC address. Okay. So then, when trying to build the address table at this switch port, then generally what happens? They try to send the echo packet in the network, which can reach to every device or every host in the network. So the attacking host then just send a frame throughout the network with the newly configured the MAC address, which is got as a legitimate user. Actually, this address is belongs to the server. So then upon this packet is received by this Ethernet packet is received by the every host in the network, and when the switch receives this frame or Ethernet packet, it examines the source MAC address, and it finds that the switch overwrites the current the address table, that table entry here, the port entry, and assigns the MAC address to the new port. So it then forward frame, which is designed for the target, has to the attacking host. So because upon receiving this, the new address port will be built for this port, for this MAC address. Suppose port 2 is built here. So that is the threat actor just alter this MAC address of the host and to match another the known MAC address. So it will find out the newly configured MAC address, and after that any traffic which goes to this MAC address, which will send by any of the user in the network, instead of going that to this the legitimate user in the network, it goes to your threat actor. So this is the address, spoofing part. So when the switch updates this the address, that this CAM address is here, then the application or service spoofing is another spoofing example of this. So threat actor can connect to a rogue DHCP server to create the man in the middle attack here. So the legitimate, it finds that the device with MAC address is the threat actor. So then it tries to connect with the your rogue server. So these are some of the IP address vulnerabilities. How they are going to be used means, while building the routing table or your MAC address table, or we call the address resolution tables. So there the actors can gain access and try to become as a legitimate information accessor in the network. So the next layer 4 protocols, and what are their vulnerabilities, that we'll try to check. So to understand this, we just check their header fields. What is there in the header field? We call this as your segments. So your application layer packets, application layer data is divided into small segments or chunks. We call segments. Segment means it belongs to your layer 4 protocol. Packet means belongs to your layer 3 protocol. Frames means belongs to your layer 2 protocol, that physical layer, and your bit stream belongs to your layer 1 protocol. Right? So in this TCP segment header, if you observe that, while some attacks target the IP address, and some attacks that targets the TCP and UDP packets, segments. So this TCP segment information appears immediately after the IP header. So the field of your TCP segment and the flag for your control bits field are displayed in this figure. That the 6 bits control field is used by the attackers to attack these, the host or the victims. So in this control bits, it uses 6 bits. So every bit is used for different purpose here. So what are those? These 6 bits are used. One bit is used for your URG, that is urgent pointer field significant. So that gives the priority for this particular packet. And another bit is used for your acknowledgement purpose. If it is a TCP, then for every packet it requires an acknowledgement, whether it is received correctly or not by the destination side. And one bit is used for the push function. Another bit is used for your reset the connection. So here this reset the connection bit is, if it is captured by your attacker can reset the connection and attacker becomes the legitimate user, and the victim is disconnected from that network. Then the another bit is your synchronization bit. So that synchronize the sequence numbers of your packets from source to destination, as we said. That is divided into smaller chunks. So sequence number is given to every packet. So on destination side, based on this sequence number, the entire message will be rebuilt, reassembled there. And the 6th bit is the finish bit, that is no more data from the sender. So finish the connection. So these are the basic header field of your TCP. So what are the different TCP services that we identified or we have discussed so far in the TCP service? One is your reliable delivery. As you know that before sending the actual data, the connection will be established between your source and destination. Once the connection is successfully established by using your three-way handshaking process, then the actual data transmission takes place from sender to your receiver. So this TCP incorporates the acknowledgement to guarantee whether the data is correctly delivered or not on the receiver side. So what are the different protocols or examples of this application layer protocol for which this TCP service providing the reliable connection is? One is your HTTP to access some web pages from your web server, and for remote connections for SSL and TLS service, and for sending a huge volume of data for uploading or downloading from the server, it uses FTP, and domain name server or domain name zone transfers are used. So these application layer protocols use this TCP connection. Whereas another one is it also provides the flow control between source and destination. If there is no flow control, then sender may send the packets at a higher rate, but receiver may try to receive those packets at a lower rate. So some packets will be dropped in the network. When some packets dropped in the network, the receiver will not give any acknowledgement for that. So if the acknowledgement is not received, then same packets will be retransmitted by your sender. So before that, during the connection process only, this TCP provides the synchronization. If the sender is able to send 1 GB of data, 1 Mbps speed, then whether receiver is able to receive that 1 Mbps speed data or not. If it receives at a lower rate, then some packets will be, dropped there. So this TCP implementation implements this flow control to address this issue that rather than acknowledge some segment at a time, the multiple segments can be acknowledged with a single acknowledgement segment as piggyback. And then the stateful communication. So in the stateful communication, as we already discussed this, for every packet, the routers maintains the state that whether the packet, what is the sequence number of the packet, whether that packet is successfully transmitted or not. So this TCP stateful communication between two parties occurs during the three-way handshake as we discussed. So before data can be transferred using TCP, a three-way handshake opens this TCP connection as, and then it starts sending the packets. So that is stateful connection. If you see in this example, in three-way handshaking, which we already discussed. So a TCP connection is established first. So then the client will the initiating the request a client to server communication session with the server, that is send synchronization packet with the sequence number and your CTL for a connection to live. So then it gets the acknowledgement for that synchronization, the sender or the client. Then the connection will be established, though both the parties agree to communicate at the same flow control. So during this three-way handshaking process, is there any vulnerabilities are there? Means yes, definitely there is a vulnerability in this case. How? The network application which uses this TCP or your UDP ports, the threat actors conduct port scan of your target device to discover which service they offer, whether it is a TCP service or whether it is a UDP service. So based on the port numbers, they can easily identify, they find out what are the difficulties are there in that. So we'll see in this the TCP attack by the attacker, the TCP synchronization will be flood into the network. So this TCP synchronization, as discussed in three-way handshaking process, that I want to establish a connection with a user, a server. So the TCP sync that flood the sync flood attack exploits this TCP three-way handshake. So in this figure, if you see that a threat actor continually sending a TCP sync session request packet with a randomly spoofed the source address or source IP address to a target. So the target device replies with the TCP sync acknowledgement packet to the spoofed IP address and waits for a TCP acknowledgement packet. So those responses never arrive. So eventually, the target host is overwhelmed with the half-open TCP connection, and TCP service are denied to the legitimate user in this case. So in the first step, if you see, the threat actor sends this multiple sync request to a web server in this case. So a TCP, then the web server replies with the sync acknowledgement for each sync request and waits to in the second stage, sending this acknowledgement replies. Once all these acknowledgements are received by your the user, the valid user, okay. So then some of the replies goes to your threat actor. So a valid user cannot access the web server because the web server has too many half-open your TCP connection because of the victim. So another kind of your TCP attack, as we just discussed, is, so then it is the TCP reset attack. So one is TCP flooding attack, which is establishing the another one is your TCP reset attack. So a TCP reset attack can be used to terminate the TCP communication between two hosts. So in this figure, if you check it out, how this TCP uses a four-way exchange to close the TCP connection using a pair of your finish the connection FIN, that is sending the finish the connection bit, that 6-bit control bit. In that, this bit will be set to 1, and the acknowledgement segment from each TCP endpoint. A TCP connection terminates when it receives and reset bit. So this is an abrupt way to tear down the TCP connection and inform the receiving host to immediately stop using the TCP connection. So a threat actor could do a TCP reset attack and send a spoofed packet containing a TCP reset to one or both the endpoints. So they think that actually the legitimate users only send this reset packet or reset bit or finish bit, but actually it is done by the attacker. So in this diagram, if you see, the first step, when the client has no more data to send in the stream, it sends a segment with the fin flag set, and the server sends an acknowledgement to acknowledge the receipt of this finish connection to terminate the session from client to your server. Then in the third step, the server sends the finish to the client to terminate the server to client session. And at the fourth step, the client responds with the acknowledgement to the acknowledge the finish from your server. So this is the reset attack that can happen. So similar to that, another one is your TCP hijack attack. Yeah, this is what we just discussed. In TCP hijacking attack, or session hijacking attack. So this is like your man in the middle attack type. So this TCP session hijacking is another TCP vulnerability. So although the difficult to conduct, a threat actor takes over an already authenticated host as it communicates with the target, and the threat actor must spoof the IP address of one host and predict the next sequence number and send an acknowledgement to the other host. So if successful, then the threat actor could send but not receive the data from your targeted device. So this is the another kind of the vulnerability of your TCP hijacking session. So then comes to the weaknesses or the UDP segment header. So as we see that UDP is your connection-less service. So UDP is commonly used by your DNS servers or DHCP application layer applications, the dynamic host configuration protocol, or your TFTP or NSF, the network file system, and your SNMP. So these are some application layer protocols which uses the service of your UDP. So they just whenever they are ready, they just try to send the data, but they don't wait for the acknowledgement. So this UDP services used by the some of these applications. So it is also used with the real-time applications such as your media streaming or voice over interface, that VoIP. So UDP is connectionless transport layer protocol. It has much lower overhead than your TCP because it is not the connection oriented and does not offer the sophisticated retransmission or sequencing and your flow control mechanism that provide the connection oriented, and does not offer this the statefulness also. So the UDP segment structure looks like this as you see in the figure. So the UDP actually divides data into datagrams, whereas your TCP divides data into your TCP segments. So, however, this generic term segment is commonly used, but it uses the datagram. So, although this UDP is normally called unreliable in contrast to your TCP reliability, so this does not mean that applications that use the UDP are always unreliable, or nor does it mean that UDP is an inferior protocol. But it means that these functions are not provided by the transport layer protocol and must be implemented elsewhere if it is required. So the lower overhead of this UDP makes it very desirable for protocols actually that makes the simple request and reply transmission. For example, like using your TCP for your dynamic host configuration protocol, DHCP would introduce the unnecessary network traffic. So if no response is received, then the device resends that request again. So these are the basic function. So here it is, if you see that it uses 8 bytes, whereas your TCP it uses 20 bytes, IP uses 20 bytes in size maximum. Right? So what are the weakness, I mean what are the vulnerabilities are there of this UDP attack? So we'll see those vulnerabilities. The UDP attack is there. So in UDP attack, it funds the UDP flooding attack, because as we said, it is a connectionless service. So UDP is not protected by any encryption. You can add encryption to UDP, but it is not available by default. So the lack of encryption means that anyone can see the traffic and change it and send it on to its destination. So changing the data in the traffic will alter the 16-bit checksum, but the checksum is optional and is not always used in the UDP. So when the checksum is used, the threat actor can create a new checksum that is based on new data payload and then record it in the header as a new checksum. So the destination device will find that the checksum matches the data without knowing that the data has been altered. So this type of attack is not widely used, but it uses the UDP flood attack. So you are more likely to see a UDP flood attack in the network. So in UDP flood attack, all the resources on the network are consumed. The threat actor must use a tool like UDP Unicorn or low orbit icon connection for so then use these tools, and these tools send a flood of your UDP packets, often from a spoofed host to a server on the subnet. So the program will sweep through all the known ports, trying to find closed ports. So this will cause the server to reply with the ICMP port unreachable message. So because there are many closed ports on the server, so this creates a lot of traffic on the segment, so which uses up most of the bandwidth. So the result is very similar to your denial of your service attacks. So these are the different vulnerabilities of of your layer 3 and layer 4 protocol, and how they are used by your attacker. So with this, I would like to stop this session. If you have any